Everyone, welcome back to our afternoon session. And we had a wonderful morning session. It was very crowded. And hopefully everybody will be back after a short break of lunch. The morning we have two wonderful talks on overall view of deep learning, how they will be able to use in neuroimaging field. Then we also have Sergey and Chaogan to discuss convolutional neural networks, how we'll be able to use it and more generalized way so that we'll be able to do cortical segmentation, classification, as well as Chaogan has this big model that allow you to upload data to actually do a prediction for AD, as well as other developmental or neurodegenerative diseases. So today, in the afternoon session, I will start with graph neural network. So I will start to discuss some graph neural networks, and particularly we deal with the data that's actually structured data. So it means like we have brain network data. So how we will be able to use it, how we will be able to build the convolutions. So we will still going to continue with convolution, but in the graph, on the graph, and how we will be deal with the functional MR and diffusion tensor images data, particularly when you start to use them to understand how brain are wiring. So I'm going to start with, this page. I really like this because a lot of medical data is in the, we acquire data in the 3D volumes of 4-dimensional images. However, and there's a lot of informative data, inherited in the 3D images, then which we can use surfaces, for example, cortical surface, to characterize geometry information of data. Then for resting state function MR and structural data, so people actually can build the graphs, and that tells us how structurally and functionally brain are connected to each other. So there's actually a graph data, and you have data defined on each brain regions, and you also have connection information, means how strong they can be connected to each other. So those are what we call the graph structured data. And certainly for those people who are interested in imaging genetics, you may deal with molecular data as well as genotype data, where you need to learn how the genes interact with each other. And those are the things are what we all call it as graph structured data. So what's the difference between the graph structured data, what is 3-dimensional images or 2-dimensional images? And the major difference is between these two types of data is actually for the structural data, it sits into the space that you don't really know how many neighbors you have. Okay, for instance, down here you show the nodes down here, and this node has actually have 5 neighbors. So that means the first neighbor, they have the neighbors that has edges that connect to them. But certain brain regions, they only have 3 connections and so on and so forth. Well, in the 3-dimensional space, if you think you always have like 8 neighbors or 27, 26 neighbors, you can actually define it very clearly. While in structured data, you don't have. And this makes it very difficult for convolution operations if you want to do convolution neural networks. And there are many studies that actually propose like graph neural networks. Then the idea is really to introduce 2 functions. One is called the aggregation function. The other one is called the updating function. So what does it do? So for aggregation function, it's really trying to assign, learn a weight among the neighbors, and this is a one hop neighbor, so means this node has 3 neighbors, and you learn the weights, then you sum together, and then they update the information down here. So you really have to think about how you will be learn all this information. And majority of simple cases, they just mainly use mean average, and because you don't know how many neighbors, the easy way to do is actually just average whatever the neighbors you have and just do the sum, do the averaging. Or you can take maximum values or minimum values. And those are the typical, very typical aggregation function people use to define. Then, of course, you have, update function. So it means that how you're going to update information to the next layer and so on and so forth. Then when the attention network comes out in the 3-dimensional images, then people start to think about, we also can start attention mechanisms and use those attention mechanisms to learn the weights and to tell people how important of each neighborhoods are. And this is actually embedding attention mechanism into our traditional graph neural networks. So again, and what is a flexible way for us to be able to do convolution? And here, I'm just talking about signals that define on the nodes. Then you can actually do these convolutions on the nodes. You can do this aggregation information on the nodes and define a graph neural networks. But for brain neuroimaging data, we do know we also have edges information, right? So there's a recent work published in 2017, and I think it's well known in the community. And this basically start to introduce edge neighbors. So the aggregation function for edge signals down here will be functional connectivity, right? That indicates how strong the brain regions are connected to each other functionally. And you can think of, for this edge, you basically have a couple of edges on this side, and also a couple of edges on this side. These are neighbors. And you can similarly define aggregation among the information that connect to all these edges together, and push the information update to the next one. And certainly you can consider more broader edges. So that means this is one hop neighbors, and this will be second hop neighbors, and you can actually aggregate information in a broad sense. So in other words, you can actually scale it based on how many layers of neighbors you want to include it inside. And this is actually become the way of this brain net CNN is introducing. So it basically introduces the edge aggregation, and that will be able to allow you to aggregate edge information and learn it through multiple layers. And eventually, the edge information will be projected into the nodes information and concatenate everything together and for prediction or regression problems. So with all this information, all the bottleneck we have is that we don't have the traditional way of convolution, like what Sergey showed this morning. So you have this traditional way of doing convolution in the three-dimensional or two-dimensional image space, where you can shift your filters in the space, and that makes things very easy. For instance, if you have the filter size of 3, and you have 9 parameters, and you just need to shift these 9 parameters and one by one, and so you will come up with these new images. This is how you're going to learn the neighborhood information from the images. Then the operation for convolution is very straightforward, very easy. It's just 9 multiplications plus 1 summation, then you get it, and it's very straightforward. But in addition, for this figure, I show, there's no downsampling, so you can actually easily do some downsampling in this regular grid as well. So it becomes a much faster operation in the three-dimensional, 2 or 3-dimensional images. And here, just give you a summary on what we see this morning. And I think we use the same website. We download the pictures from there. It's very good illustration. For example, if you have color images, if you have color images down here, 3-channel color images, and you have the filters, and you can actually do shifting the filters. And here we have downsample of 2, so basically you actually can skip voxels, and you can become smaller scales, and you can do the filtering, and you can also do a multi-scale learning as well. So now what we really want to do is actually how we will be able to translate this kind of operation in a graph manner. So in other words, how we will be able to automatically define aggregation or learn the aggregation function, and regardless of how many neighbors they have, regardless of how these people are connected to each other. And so that we'll be able to learn the signals on the nodes, on each of the nodes, and then they will be able to go on and learn things from there. And you can actually learn from n layers of the neighbors. It's called n hop of the neighbors as well. So we really want to borrow the notion of Euclidean space, like three-dimensional or two-dimensional or one-dimensional space, convolution information. So how we will be able to do that? So just for those, I believe everybody has some sense of signal processing. So this is This is one-dimensional signals and defined as a function of time. And you can actually expand this information as a linear combination of sine and cosine function. And this is what we call the typical Fourier transform, okay? So why I want to talk about Fourier transform? Once you have this basis function, right, sine and cosine function, the convolution becomes very easy. You can actually just learn define some coefficients in the spectrum domain, and you will be able to find the filters there. So how we will be able to do on the surfaces, the surfaces down here is cortical surface. I show you signals like cortical thickness, curvature information, functional connectivity in occipital lobe, and those are the information on the cortex. And here in the computer, so we basically characterize the neural networks. We basically characterize the surfaces as triangles. You have nodes, vertex information, and the edge information is really trying to form the geometry information of the cortex. And if you have signals defined on that, then how we will be able to study, do we have some basis like sine and cosine function on those surfaces? And idea is, the answer is yes. Actually, we can build similar sine and cosine functions on those cortical surfaces, and so that you can actually do signal processing as what we do in the Euclidean space, one-dimensional space, two-dimensional space, and three-dimensional space. You can do anything you want to. So the way we do this is actually we borrow the Laplace spectrometry operator that allow us to be able to learn the geometry of information of underlying geometry for the cortex. And here, the delta down here is the Laplace spectrometry operator, and psi here is the eigenfunction. So the sine and cosine function we want to compute. U is the point, the vertex, on this piece of surface. Then here, the second equation is just normalization, and the third equation is just make sure if you have boundaries, all the network we study has boundaries, and you cannot let your signals go out of the boundary. So it basically has to be within the piece of cortex. So you can compute this Laplace spectrometry operator, the eigenfunctions easily. Well, this the delta down here, the Laplace spectrometry operator, can be interpreted as the area as well as the angle information of the surface, which is the true geometry of the surface. Okay. Just give you a simple look how they look like. So you have a sphere, and for a lot of people probably already see this is called spherical harmonics. It's also the eigenfunction from Laplace spectrometry operator. And you have positive and negative, like a very slow change. So red is positive and blue is negative. And once you go to higher order, and it becomes a blue and red alternating much faster. So you have higher frequency signals coming from there. And you can build this for any part of the cortex, or even the functional graphs and so on and so forth. So you can build this basis function on those graphs. So how we will be able to do a signal processing using those basis, Laplace spectrometry basis function. So the same as what we see in the one-dimensional space, any signals down here, you can actually reconstruct it using a linear combination of those spaces. So there's a coefficients, you just need to give coefficients and sum all these spaces together, and you will be able to generate new signals. Okay. So now I'm going to use this notion to introduce the spectrum filters. So you have basis function. You have basis function psi down here. So any signals, for example, in cortical thickness, it's the signals we are studying, you basically can expand it as a linear combination of this equation. Okay, that's a Fourier transform. The C here is the Fourier coefficients, in the similar concepts, right? So now we can actually define a spectrum filter. And this H is a spectrum filter. Lambda is really indicates the frequency on the surface, the signal frequency on the surface. So basically now if you define this filter, and you can think of, we have our signals down here, and this is a Fourier transform into the spectrum domain, and this is the spectrum filter down here in the spectrum domain, and you have this basis function. You can do an inverse transform to transform the signals back to the original cortical surface space, and that becomes very, very easy and straightforward. So that means we only need to know how to design these spectrum filters in the spectrum domain. Okay, now how we will be able to do that? So basically, if you think we have a big surface, like a cortical surface, down here is a whole cortical surface, and some people actually use more than 10,000 points to represent this cortical surface, then the computation for Laplace spectrometry eigenfunctions is very expensive. So what we do is actually we can have a very nice approximation approach to be able to approximate the signals down here. And we basically can build an approximation for spectrum filters so that we don't directly need to compute the sine, cosine, this Laplace spectrometry eigenfunctions on this big cortex. So what do we do down here? So I just rewrite the previous convolution equation into this simple equation down here. You have your signals, like for example, cortical thickness defined on the cortex F down here. And lambda is their Laplace spectrometry operator. T is a polynomial, so it can be first order polynomial, second order polynomial. So that means you only need to compute the Laplace spectrometry operator, which is very fast to compute. And the coefficient C here is something unknown, okay, that controls the shape of the spectral filter. So in convolution neural network, these coefficients will be the one we want to estimate through the learning procedure, through our training procedure, okay? And if you think, if we use polynomial, capital K down here is second order, so this means you only need to have 3 parameters to estimate it. So in other words, compared to a traditional two-dimensional convolution filters down here, 3 by 3, you need 9 parameters. In our case, and the filter, the number of parameters we need to estimate for the filter is actually K plus 1. In majority of cases, we only use the first order and second order. In other words, your filter only need to have 2 or 3 parameters to be able to define very nice filters in this cortex. So I'm going to just show you, you can use a variety of polynomials to be able to actually estimate this. And here are just some examples. You have Chebyshev polynomial, Lagrange polynomial, Hermite polynomial. And the first column showing down here is the first order polynomial fitting. The second column shows fourth and 10th order. Here's our original signal. Okay, so we just have simulation data down here. So here is our original signal on the top of hippocampus. And if you use first order polynomial to do the filtering, and you can see the size is relatively small, and you actually kind of blur your signals to the outwards. Okay. Once you go to a higher order of polynomial fitting, then the spatial coverage becomes bigger and bigger, and that's the scaling information you want to understand. Okay, so now if we have this type of convolution, and you can just plug into traditional convolution neural networks by replacing the convolution operators using the filters I introduced now, and you can actually, this can become a graph convolutions, graph convolution neural networks. So here is an example. We have cortical thickness data defined on the cortex, and each cortex is actually triangulated meshes. So you have vertex, and each vertex has a number. This number indicates this location's the thickness, the cortex, the depth of the ribbons down here. And here we just shows, we use Alzheimer's data and to actually try to differentiate, controls versus AD, or the early MCI, mild cognitive impairment, or the, late MCI cases. And you can see the accuracy is relatively good. And compared to just using a stretch, the cortical thickness to be 1D array and just do a simple convolution. So the performance is way better than that. And even for compared to a structural MR data, of course, I didn't compare with Chao-Gan's robust, 3D CNN network. We should plug in down here as well. So basically, you can see you can reach reasonable information down here. So I guess, there are a lot of potentials when you incorporate geometry information into the network, then and you can easily do a convolution and on the cortex, and so that allow you to be able to learn the geometry information as well as some feature information, and together to be able to do a classification. So now, let's come back to this graph again. So, so far, I only introduced the graph convolution, so the convolution operator on the nodes information. In other words, you have only signals defined on each of regions. So, and I use the cortical thickness as an example down here. So you basically will be able to use those information to do a convolution. However, majority of us down here, we start to use the resting state function MR. I think almost every neuroimagers use the resting state function MR nowadays. And you know we also have signals down here, which is colored in red. So it means that you have signals that characterize functional connectivity information between regions. And you also have signals on the nodes, and that can be functional time course data, or some other information, for example, cortical thickness information on that. So in other words, you have functional connectivity, but you also can have nodes information that related to structure information, okay? And then how we will be able to do convolution for both signals, right? So you have signals on nodes, you have signals on edges. So I'm going to extend the convolution operator I just introduced now to a more broad sense. You can actually study very complex connections among nodes, edges, or even triangles and tetrahedrons. You will be able to use this general framework to do convolution. And of course, you can do a graph structured data neural networks as well. In addition, I'm going to introduce a graph pooling approach because pooling is not easy. We don't have a regular grid, so you can actually just downsample the graph by factor of 2. Unfortunately, it's not that easy to do in such a way. So I'm going to introduce a pooling operator, how you will be able to aggregate information from edges, nodes, and different levels, and determine how important they are, and before you do the pooling. And finally, I'm going to show you we actually use that. We will be able to actually interpret all the data as well. So how are we going to do with it? So again, so we're going to be more generalized to our data. So you have data like a graph showing down here. Here you have 6 nodes, and the nodes is called the zero-dimensional simplex. And you have edges, and down here we have 6 edges, and it's one-dimensional simplex. And you can even study 3 brain regions connections, which is triangles showing down here. And this is called a 2-dimensional simplex. And you can study 5 regions, 4 regions, 5 regions, and so on and so forth. You can actually extend it as many as possible. So for those who are interested in higher order convolutions among multiple regions, and you can actually go for higher order, higher dimensional simplex. So we're going to introduce the concept of a topology down here. So what does it mean? So topology really means how the nodes, edges, and triangles are connected to each other. And this is a simple operator called the boundary operator that allow you to really know which are the nodes connect to which edges down here. So for example, in row down here, you have 6 nodes, and they will tell you first nodes where it is. And the column down here is the edge information. So it really tells you the first nodes are actually involved in the first 2 edges, okay? And the second node is actually involved in this edge, and so on and so forth. And you can actually extend the boundary operator again into a higher order boundary operator. But each time, it basically encodes the link between this current, simplex, dimensional simplex versus next simplex relationship. Okay, and you will be able to know how the edge coming from triangles, a triangle coming from tetrahedron, and so on and so forth. So you'll be able to actually really know all this topology connection information about your graph. So once you have this, remember our case is trying to figure out what is sine and cosine functions, right? So your sine functions on nodes, you have sine function and cosine function on edges, you can have sine and cosine function on triangles, and so on. And here is just an extension of Laplace by Chomsky operator. It becomes hard Laplacian operator. And the hard Laplacian operator really can build it from what we just introduced, the boundary operator. Okay, it's also symmetry operator, and they allow you to basically, it's a symmetry operator so that it allow you to compute the eigenfunctions. And those become the eigenfunctions on nodes, or edges, or triangles, and so on. So for instance, for the zero order hard Laplacian operator, this is exactly equivalent to the graph Laplacian okay? And the second order, the first order hard Laplacian is just becomes you want to define the sine cosine function on this edge information, okay? And that becomes very straightforward. If you have sine and cosine functions, and we can easily build the filters in the same way as I just introduced. Again, in the spectrum domain, you have those, for example, we are looking at edges. You have sine function and cosine function on edge. And here's our true signals, Fourier transform, functional connectivity, information transform in the spectrum domain, the coefficients down here. And here is the filters we want to figure out in our deep learning framework. So if you have that, again, we can actually use a simple polynomial approximation to be able to approximate those spectrum filters. So you only need to estimate a few parameters from that. Again, here, so you have t down here is the polynomial, theta is the coefficients you want to estimate, and those are the only parameters you need to estimate from this framework. So I'm just to show you some examples. Now we have signals at this particular edge, and if you use a first order polynomial to do the filtering for the edge, and you can see, so this color is a little bit big, so you can see you have signals in the center, then actually spread it to the first hub neighbors of this edge. Then if you use the second order, and the signals actually spread it 2 levels away from that center edge. And then you have first order, and certainly the information, the filters become much broader, and so on. You can also achieve this just through the edge filters. So it means if you do this 4 times, using the first order polynomial to do so, and you actually get a similar result. And this is very nice because in deep learning, you want to have deep layers, okay? Rather than have very big filters and learn once, you actually want to learn multiple times. It gives you a flexibility to learn the spatial, spatial information across the entire graph. Okay, so now I'm just giving you a very simple example down here. We have a traveling salesman problem, and for those of you who know this problem, so it's actually an Anhart combinatorial problems, and the salesman traveled all the cities on this graph, and this graph is showing all the cities down the graph. The right line shows the connections between the cities, and the salesman is trying to go through all the cities with the shortest path, so it means like shortest distance, and they save energy on that, right? So it's pretty typical NP hard problem, combinatorial problems down here. And what we do down here is we just basically use very simple filters. So here we have the graph, the map is the graph, right? So cities, you have x, y, z coordinates in the map, right? So you know where the location of the city. So your signals on each nodes down here is city, is x, y, z. They are geometrical coordinates. Then the edge information is really the distance between the cities. And so they basically, you are trying to figure out, we were trying to figure out how to trim down the edge, and so that we'll be able to find the shortest path. So what you see here, once we gave the input signal down here, we just do the no signal filtering and edge signal filtering, nothing else. Okay, just a filter approach. We use deep learning to learn a couple of layers of these filters, and filter information of x, y, z, and filter information of the distance between the 2 cities, and you will be able to find solutions down here. So here is just an illustration. So you can see after a few layers of filtering, and the edges, the connections between the cities that's not important has become much weaker. And here you can see our estimated approach, the pathways are very similar to the ground truth, even though we still have some bit of errors down here, but actually that's much faster than directly solving NP hard combinatorial optimization problems. And here just give you examples, just using filters, they actually allow you to highlight what are the edge information are very important for this study, for this problem. And here is just summary how the edge signals is changing and no signal is changing across the learning process. So now let's come back to the brain problems, right? So for brain problems, And even though we may learn our brain networks, by aggregating a lot of voxels into brain regions, then we just learn small networks. For example, 200 brain regions, you have networks of 200 times 200 matrices. But the edge information is still quite a lot, right? So the 200 times 200 divided by 2, so you still have about more than 10,000 edges information you need to learn from the graph and a graph neural network. So in order to be able to reduce the dimensionality of the data, as well as trying to learn multi-scale information, we actually need to think about some pooling process, as we see in this morning's talk, right, for traditional convolution neural network. So we also need to do some pooling process on the graph. So how we will be able to do that? And remember, we have information on the brain region nodes. We also have the information on edges, which is functional connectivity information. And both information are influencing each other, right? It's not just simply you can just remove edges. While the nodes information is very important, you want to keep both information simultaneously to be able to learn simultaneously. So what we do down here, we actually borrow the idea of transformer. Okay, you do have transformer information down here, so we need to learn the keys, Qs, as well as the value information in the graph. But in the meantime, what we want to do is actually learn the information across edge and nodes. Okay, so you can see you have this self-attention. Self-attention really means if you just learn the node information by itself. Okay. And this self-attention, it basically can learn the edge information by itself. However, you have these crossing terms down here. And this one is really trying to learn the edge information, project this into nodes, and concatenate those edge and nodes information together, and to learn and those information together in order to determine which nodes information are more important. And similarly, you project your nodes information to edge down here and aggregate the edge information together, and to be able to learn the two information together and decide which edges are more important. And you can actually use those importance to actually trim down the edge and nodes, and so that you can actually reduce the size of the graph. And that reduces the size of the nodes, number of nodes, as well as the number of edges. Down here. And it's a pretty robust approach. So just give you an overall view. So if you have data structure, graph structure data, and particularly if you think about the setting of functional connectivity, and you have a functional time series data on the nodes, and you have edge information that's related to functional connectivity, and both the information you want to learn, and for prediction problems, and you have the filter layer, and you have a projection layer, so that means you can project node information to edge information to nodes, and you will be able to do attention down there, as well as do the pooling. And you can repeat this whole block many times, and it becomes a deep neural network learning framework. So you can actually do this multiple times as well. So I'm going to use a couple of minutes to actually illustrate some examples we do. And the first example, I'm going to use a molecule example, and quite a number of people who are working on drug discovery applications. And here is just molecules, and molecule is formed by atoms, and each atom is the nodes on the graph, and atom has properties that you can actually assign to it. And you also have edge information. Edge information really tells the bonding energy between the atoms, how they will be able to form molecules down here. And here we do a regression problem. So we want to actually learn this information and to be able to predict the solubility of these molecules. And solubility is a very important parameter for drug discovery. So what we did is actually using our framework, as well as compare with a traditional graph neural network, which is the one I discussed at the beginning of the talk. You can just simply average all the information by simply taking the average and update the information and learn multiple layers. And here is the attention neural network. And here is gated, similar to the attention, but it's gated mechanism. And here is this graph transformer information. And this is our approach. So you can see there's color down here. And from blue to red is actually solubility increases in this dimension. Okay. You can see overall, all this approach will be able to allow us to see from lower value to higher value of solubility. But in our example down here, you actually see 3 clusters as well. So when I saw this figure, I actually don't know why we show 3 clusters, while the other approaches actually shows more like 2 cluster information. So I asked my student to actually dig into it, and it turned out these 3 clusters actually related to another parameters, which is the parameters of synthetic accessibility. It's really related to underlying connections of all these items, how they will be able to form this molecule. And you can see by embedding a good information of topology and structure information, then you'll be able to get actual bonus from this application. So last example I'm going to show is brain imaging data. So now we will have a very, very large data. So we basically use both PNC, Pennsylvania data, as well as ABCD data. And those are all adolescents data. And PNC actually has a broader age coverage, and this is actually considered as our training data sets. So we have a morphology, we have thickness and surface area, and also a subcortical volume. Then we also have functional and resting state functional metadata, as well as diffusion weighted images. We use both images to construct functional and structural networks. So if you put those data together, and we actually start to learn whether this information will be able to predict for the general psychopathology. Okay, and general psychopathology is a continuous variable, so we don't characterize disease as 0 and 1, because in the early age, neurodevelopmental disorders is very complex. It's comorbid, so it's much easier just to learn how the psychopathology are characterized in the continuous manner. So we basically use this network to predict this general psychopathology. You can see in morphology data, and here's the cortical thickness, surface area, all together down here. And this is structural connectivity from diffusion weighted images, and this is from resting state functional map. So you can see 3 modalities achieve pretty much similar accuracy in terms of correlation with the original data. Then you combine 3 altogether, it actually increases almost by another about 20% of correlations down here. And here, if we directly use the trained framework from PNC, we can actually do a small learning, just trying to align the harmonize data together. So basically, and you basically achieve similar accuracy as what you see in the PNC data. Sorry, so slightly lower, and this is mainly because ABCD data only covers the age range of 9 to 11, so it's not so broad age range. So lastly, if you see how the attention map, which are the brain structures and morphology information and functional connection information that, can be replicated in both populations, and you can see there are huge overlaps between the 2 cohorts. And for morphology-wise, it's reached to about 0.6 correlation, and in terms of which are the region contributes to general psychopathology, and similarly for functional connectivity as well as structural connectivity. And this is a very, very powerful tool, and we will be able to demonstrate it in the afternoon session if you are interested in that. So my student will run the demonstration later on today, and you can actually try it out. We also have a web version. You'll be able to just play with it and with your laptop. And so it's very straightforward. So without further ado, and today I actually give you a general framework that allow you to be able to do a convolution on node signals, edge signals, or even higher order, complex, simplex, complex, you can actually do the filters on a more higher order, higher dimensional simplices. And that can be easily achieved. And number of parameters you need to estimate is very small, and it's controllable. So this, I think it can be very useful for those who are very interested in learning brain organization. So without further ado, I'd like to thank all my funding agencies and many students who actually contribute to data processing for the work I presented here. Thank you so much. So we do have time for questions if some of you have questions for me. So.
Your slide showing the with the architecture where you pull the node and edge data together. Could you also do that, like, to combine data from different modalities? Like the most obvious example being like just edges from resting data from RAI versus edges from DTI data into.
Oh, can
Have
sure.
you tried doing that?
Yeah. So in other words, you basically, your edge signals will be 2 dimensions. For example, you have structural connectivity, then you have functional connectivity. And it's like, in the computer vision, it's like RGB values, right? You have 3 channels. So you know here you have 2 channel information. You can have as many channels as you want. Yeah.
Thank you. It's really interesting methods you introduced. I was just wondering, when you do all the analysis in the spectral domain, you may miss local information, specifically introducing some Gibbs phenomenon. Would you be able to address in this attention system?
That's very, very good question. So this is a beauty about this polynomial approximation approach. Yes, indeed, in spectral domain, if you just define convolution filters and so on and so forth, you may have a lot of problems regarding localization problems. And I actually don't have enough time. This actually have a systematic theory. You can actually define in this manner. Actually, it's really waveless manner. So it means that you can localize the signals and you can control the size. And this is why I show the figure down here. So if you have order of 1, it's only actually spread 1 neighborhood out. And if you have order of 4 of polynomial to do the fitting, you actually only spread to the 4th layer of neighbors. Okay, so you can control the localization. Okay, yeah. So I do miss middle part because of time. I didn't talk about anything related to wavelets. And this is actually a wavelet construction.
Thank you. Can I ask
another
quick question?
Yeah.
Sorry. I know polynomials are very good in terms of speed, but they are limited in case of all the possible filters. For example, you can't have really a high-pass filter easily with polynomials, yeah? Because it's a sigmoid function.
Yes, that's true. That's true.
Is there any way to address that?
So I would say in general, we actually learn all the low-pass information, cross and the high-pass. We always think it's like noise signals down there. So actually, I don't know whether we need to learn high-frequency signals and so on and so forth. But perhaps if you do, then you have to change your lambda, the omega down there. Then they can cover the high frequency. Yeah.
Thank you.
Thank you.
Hi, thank you very much for a wonderful talk. I was just curious about how this can be expanded or extended to a graph within a graph, for example. If you're trying to have an individual graph prediction, but in order to also account for a group level, would you be able to kind of extend this methods to graph within a graph?
I guess what you're saying is actually you have big graph, then you have small graph, then is that possible? So it's possible, basically you can just build your Laplace spectrometer, L down there to be in that local location. Yeah.
Thank you.
Thank you. I think because of time, if you have questions, we will stay here for the practice session. So I'd like to introduce our last speaker. Tom Nichols, and actually I knew Tom since I was a graduate student, but we were all very young when Paul organized workshops at Loney. So many times, many years ago. So, but Tom is the statistician who really have contributed to the field a lot. I'm pretty sure a lot of you guys use a statistical approach that he developed over the years. And I really want him to comment on deep learning versus statistical approach. I believe both works well in the community, but we really need to understand how we will be able to choose one tool versus another. So let's welcome Tom.